This video is about Friedman two-way analysis of variance by ranks. At the end of this lesson, students should be able to determine if we may conclude from the sample that there is difference among treatment effects by using Friedman test. The Friedman test is a non-parametric analog of the parametric one-way ANOVA repeated measurement. The sample of population are normally distributed. For the assumption, number 1, the data consists of B mutually independent samples which are blocks of size K. The typical observation Xij is the jth observation in the ith sample, which is block. Rows represent the blocks while the columns are called treatments. Number 2, the variable of interest is continuous. Number 3, there is no interaction between blocks and treatments. And number 4, the observations within each block may be ranked in order of the magnitude. This table 7.1 shows data display for the Friedman two-way analysis of variance by ranks. We know that the column represents the treatment, which is K, and the rows represent the blocks. We move to the hypothesis. H now, median 1 is equal to median 2 is equal to median 3 and until equal to median of K, which K is rows. H1, at least one equality is violated. The test statistic. Firstly, we need to convert the original observations into ranks. In the Friedman test, the observations within each block are ranked separately from smallest to largest. Secondly, we need to obtain the sums of the ranks Rj in each column. The Friedman test statistic is defined as the equation below. This is the equation. There is two equations in the Friedman test, which is equation 7.1, which is this equation, and equation 7.2, this equation. We need to show that equation 7.1 is equal to equation 7.2. We know that the summation of j equal to 1 until k of Rj is equal to k over 2 times with k plus 1 and all time with b. And the second equation is the summation of j is equal to 1 until k of 1 is equal to k. So we will use these two equations and substitute it into the equation 7.1. After we substitute it, we will expand it and we will get this equation, which is equal to equation 7.2. So from this step, we know that the equation 7.1 is equal to equation 7.2. In decision making, we will reject the H null if the statistical values is greater than the critical values, where the critical values can be referred to the chi-square table. Now, we will do some example. Example 1. Hall et al. Compared 3 methods of determining serum amylase values in patients with pancreatitis. The results are shown in table 7.2. We wish to know whether this data indicate a difference among the 3 methods. We will be given alpha is equal to 0.05. This is table 7.2 that shows the serum amylase values, enzyme units per 100 ml of serum in patients with pancreatitis. And we know that the specimen is the block, while the methods of determination is the treatments. There is 3 treatments, which are A, B, and C. And we know that there is 9 blocks. So for the hypothesis H null, median A is equal to median B and is equal to median of C. H1, at least one equality is violated, which is our claim. For the test statistic, we know that the block is equal to 9 and the treatment is equal to K. And we need to convert the original observations into ranks. So we will have this table. We'll rank it according to each block. Block 1 until block 9. Then we will get the summation of column A, which is RA is equal to 19.5. RB, summation of column B, is equal to 9. And RC is equal to 25.5. By using the equation, we will use K is equal to 3 and B is equal to 9. And the 3 summation, which is RA, RB and RC, we will substitute it into the statistical equation. Then we will get the statistical value is equal to 15.5. In decision making, we will refer it from the table chi-square. We know that the alpha is equal to 0.05 and the treatment is 3. So when 1 minus by 0.05, we get 0.95, and when k is minus 1, we will get 2. So we use this chi-square 0.95 and 2, we refer to the table. We get 5.991. Since 15.5 is greater than 5.991, which the statistical value is greater than the critical value, then we must reject the H null. In conclusion, there is enough evidence to support the claim that the three methods do not all yield identical results. Now, we move to example 2. In order to assess the effect of different amounts of cobalt on the tensile strength of steel, researchers conducted an experiment employing a completely randomized experimental design. The treatments consisted of 4 levels, expressed as percentage of cobalt, and the 8 crucibles in which the alloying process took place served as the blocks. The tensile strengths in the thousands of psi of the resulting 32 specimens of steel are shown in table 7.4, given the alpha is equal to 0.05. This is table 7.4. It shows that the tensile strength of steel for 4 levels of cobalt and 8 crucibles. So we know that the crucible is the block, while the treatment is the percentage of cobalt. The percentage of cobalt have A, B, C and D treatments. We have 4 treatments and we have 8 blocks. The hypothesis H null, median A is equal to median B is equal to median C and is equal to median of D. For the alternative hypothesis H1, at least one equality is violated, which is our claim. We move to the test statistic. We know that K is equal to 4 and B is equal to 8. After we convert the original observation to ranks by each column, we will get this table. So we know that the summation of column A, column B, column C and column D, which is RA is equal to 14, RB is equal to 19, RC is equal to 27 and RD is equal to 20. By using the statistical equation, we will substitute K equal to 4 and B is equal to 8 into the equation. We also substitute the summation of which is RA, RB, RC and RD into this equation. So we will get 6.45 as the statistical values. In decision, we know that the alpha is 0.05 and K is equal to 4, 1 minus by alpha, we get 0.95, and k minus 1, you get 3. And we will refer this in the chi-square table, which is here. We get 7.815. So since 6.45 is less than 7.815, then we do not reject the H-null. So in conclusion, there is not enough evidence to support the claim that there is treatment differences. There is 3 exercises that you can try. Exercise 1 is about the effect of treatment drugs on reaction time of human subjects. The second exercise is to determine the plasma epinephrine concentrations during isoflurane, halothane, and cyclopropane anesthesia in 10 dogs. And the final exercise is to investigate the effect of different motivation levels on measures of food getting dominance in the laboratory rats. So this is the table for exercise 3, and you all can refer the solution in this link. Thank you.